Okay, let's have a look here at this one. So a triangle is isosceles if and only if the angles opposite the equal side are equal. This if and only if theorem, or if and only if theorems, means that the theorem goes both directions. That is, a triangle is isosceles implies the angles opposite the equal side are equal, and backwards is true. If the angles opposite the equal sides are equal, then it must be isosceles. Remember, the definition of isosceles is that two of the sides are equal. And I guess we're proving that also equivalently means two of the angles are equal. So because we have to go both directions, I'll split the page in half. So we'll say we're given the triangle here like this. A, B, C, and it's isosceles. So all we know is that these two sides are equal. And we're required to prove that the angle A, B, C is equal to the angle A, C, B. Now, we start off by saying that the triangle A, B, C is congruent to the triangle A, C, B. Actually, I'm not going to have enough space, so I'll have to go over. So there's the triangle A, B, C, and there's the triangle A, C, B. And they're congruent. Now, we know, it's known that the length of AB equals the length of AC because it's isosceles. Actually, I guess what I'm trying to prove is that these are congruent rather than I'm telling you they're congruent. So I'll just delete that statement for the moment. And I'm going to, rather than say they're congruent, I'm going to say consider the triangle ABC and ACB. And ACB is the same as ABC, but it's just been flipped around. So we know that AB equals AC because it's isosceles, and we also know, it's known that the length BC is equal to the length CB because the length doesn't care about the start and the end point. And also the angle BAC, that's the same as the angle CAB, for a similar reason that it doesn't care about the order. So what we've shown is that this side on this triangle is the same as this side on this triangle. We've also shown that this side is the same as this side, and also that this angle is the same as this angle. So what we've proven now is that the triangle ABC is congruent to the triangle ACB. And if those triangles are congruent, then that means the angles here matches the angle here, and the angle here would match the angle here. But let's look at the left one. The angle ABC, that matches the angle ACB. So that ends the first proof, starting from here and going to here. Now we want to look at the converse. So if I just go back in time. and start with the fact that the angles opposite the equal side are equal. So now we're looking at the converse. So this angle and this angle are equal, and that means we're required to prove that the length AB equals the length AC, because they're the sides opposite the equal angles. So if the angles opposite the equal, if the angles opposite the equal sides are equal, then the triangle's isosceles. So I think I might want to rephrase this so I'm not quite having the statement of the equal sides in it, because isosceles already means equal sides. So I wonder if I can just rephrase this slightly. A triangle is isosceles if and only if the angles opposite the equal sides are equal. I can't really naturally rephrase it, can I? All right. I'm not saying at this point AB equals AC. That's what I need to prove. All I know right now are that the angles are opposite. Perhaps it might be a little bit clearer if I just split the if and only if into two statements. A triangle is isosceles if the angles opposite the, perhaps I should say, claimed equal sides are equal. That might fix it up a little bit. And then vice versa. If the angles opposite the claimed equal sides are equal, then the triangle is isosceles and those sides really are equal. Yeah, I think putting in the claim is probably not an elegant way, but it clears up any confusion. Okay. So I need to prove that AB equals AC. Okay, let's try the same trick as before. So we'll draw the triangle ABC, and then we'll draw the triangle ACB. Okay, and we know that the angle ABC, that's equal to the angle ACB. That's given. Okay, we also know that the angle ABC is equal to the angle CBA, because it doesn't care about the order. So we've just shown that this angle ABC, I wrote ABC, yeah. So that's still this angle, is also the same as this angle here. Okay. So therefore, and what's left? So I can say that the angle ACB, which is this angle here, that's equal to the angle BCA, again because you can reverse it, so BCA is that angle there. So this angle I've shown is the same as this angle, and I've shown that this angle is the same as this angle. So that means that the angle at the top has to be the same as well. BAC equals the angle BAC CAB. So this angle is the same. So all the angles are the same. So if we could just show that one of the sides are the same, well, obviously the length BC equals the length CB. So I've just shown that this length and this length are the same. So that means that I've shown that the triangle ABC is congruent to the triangle ACB. So that means I've shown that the length AB is the same as the length AC. That I've shown that this length is the same as this length because they're congruent. And likewise, this length here is the same as this length here, and so on. But it was enough for me just to get to this statement. Okay, Q, E, D. Okay, so for these guys here, all I've done was just permute the letters or reverse the letters. And this one here is, again, the same reason. BC and CB are the same. So that's all the same logic for those lines here. So I've shown that they're congruent. Yeah, so really very similar. Very similar.